It's a fantastic place for working, by the way. The white noise, and there's no way to escape the laptop. So, and there's no fridge nearby. So thank you for coming. So today I want to tell you about how to verify computations without re-executing them. And for that, I want to illustrate this by discussing what I call the re-execution problem. I'll do it through example. So how many of you have heard of Ethereum? It seems like nearly everyone. So as a recap, Ethereum is a popular smart contract system, has many, many users. Not all of them speculators. Some of them are, they actually do something interesting. And at a very high level, the way the system works, you have users that produce transactions. Okay, these transactions are commands that invoke functions of so-called smart contracts. You can think about them as a state machines. Okay, they have a state, they have methods, and these transactions just invoking methods that might mutate the state internally as a function of whatever the transaction included. And separately, there is a network of nodes. It's a peer-to-peer network that will process these transactions and update the overall state of the relevant smart contracts. So it's something like this, where you have a so-called blockchain that records all prior states of the system. And the nodes in the network will kind of propose a new state from the old state as a function of which transactions were produced by the users. And this new proposed state has to be confirmed by all other nodes in the network. So they're going to say, hey, thank you for the proposed new block. Let's check whether this new proposed block really is a reflection of applying all the user transactions in this block. So they have to rerun the computation to make sure that it was correct. Okay? And if all the nodes, let's say, agree, or enough of the nodes agree, like a majority, then it is appended to this ever-growing log of sort of states of the network. Okay? So as this picture shows, the same computation, which corresponds to kind of reflecting the new state of the system as a function of transactions, is rerun by every node in the network. I checked yesterday how many nodes are kind of participating in the Ethereum network is above 7,000. So the same computation for every block is rerun by over 7,000 nodes. Okay? So this is rather inefficient. For example, it means that the entire system is bottlenecked by the weakest node. And in fact, because of this, and to prevent denial of service attacks, not only as a user you can sort of propose a transaction, or if you want to kind of issue a transaction, you have to pay for it. And the more expensive of a method you call, the more you have to pay for that transaction, because otherwise you could just kind of put in this very expensive computations that everybody has to run. Okay, so you have to pay for this every computational step. Okay, using the notion of gas in Ethereum. It's of course a caricature of the system. There's a lot of detail that I'm left out, but at a high level, this is the point. Okay, so this is a real-world system where computations are rerun all the time. Okay, I'll give a different example of a re-execution. And of course, here the question is, can we avoid re-execution? Right? That would be nice. I give a different example, completely different, where you want to rerun computations. So it's about exchanges. So a digital asset exchange is a platform that enables the trading of digital assets. For example, cryptocurrency is monotone. You can have like tokens that represent ownership of assets like art or properties. And examples that some of you may be familiar with: Coinbase, Binance, Kraken. How many of you have heard some of these names? Well, still like, I would say about half, okay? So these are examples of exchanges, okay? Now, an exchange, to make it convenient for users to trade assets, they hold their assets. So actually you give up custody of your assets, you kind of transfer ownership of your assets to the exchange like you would for a bank, right? You go and deposit cash at a bank, now they own it, and they're maintaining some account for you in a database. Something similar happens here, where you go and deposit your digital assets and you become an entry in the database. Okay? These are businesses, they're for-profit businesses, and they take these assets and go and invest them, okay? And so at a very, very high level, by taking on your assets and holding them, they take on liabilities, right? Because they owe you that money or those assets, all right? They also have some reserves, right? Now that they have these assets, potentially together with other assets as well, right? They might make money on commission fees, they might make money on custody fees, right? They might have some other, or money that is coming from investors. All of these forms their reserves, right? And an exchange is solvent if it has more money than it owes. Okay? Clear, right? It would be nice for exchanges to be solvent, and it would be nice to check that all the time, right? Can we check at any moment in time or regularly that an exchange is solvent, right? That would be a good thing, right? However, even though this is a straightforward computation, sort of tally up all of the liabilities and tally up all the reserves and compare these two numbers, this is not a computation that others can do. Like I, as a user, I would like to do it. I would like, I don't know, every morning to wake up and run this computation and make sure that the exchanges where I have deposited my assets are solvent. Even though this is a simple computation, I cannot do it. And the reason is that the data involved is private. Maybe the exchange, as a for-profit business, doesn't want to reveal all of its assets, where they're stored, what they're doing, right? Also, this computation involves other users' assets as well, about which maybe I shouldn't know anything about, right? So, without getting into details, this is a computation that, even though it's straightforward, all other inputs are not known, let's say, to the general public, but they're only known to the entity that maybe I don't trust necessarily to kind of be solvent all the time. Have any of you read about cryptocurrency news like last week? So guess what? Sometimes exchanges are not solvent. What happened, there was a big exchange known as FTX where they moved some of their reserves onto other sister companies and they invested them into risky bets, okay? The risky bets, for one reason or another, ended up sort of having a value that greatly diminished over a short period of time, and the exchange was left insolvent and now has declared bankruptcy. Okay, this happened over a course of maybe 72 hours. It's a very quick turnaround, okay? It would be nice to check an exchange's solvency, right? And this is another example of re-execution of computation. Okay, these are just two real-world examples. What I want to do now is just state the problem a bit more abstractly, okay, of the re-execution problem. Say you have Alice and Bob, that where Alice has some algorithm that he wants to run on an input X for some number of steps, and at some point he gets a result. Okay? Bob is interested in double-checking that this is indeed the answer. Okay? One option is to just rerun the computation, and then that's it. Bob can either establish this claim, the truth of this claim, or not. Right? So re-execution can be an option. However, as we've seen, there might be situations where it is inefficient. Maybe lots of people are interested in this result, they do not trust one another, and they all have to run this computation. Right? This is what happened in Ethereum. Another example is that maybe the computation is so complex or so kind of resource intensive that maybe Bob, even though there's just one Bob, he cannot rerun it. Okay? Maybe it's an IoT device and doesn't have the resources for it. Okay? As a final example, maybe the computation involves private inputs. This was an example of what happened in the exchange, right? It was like a whole computation that involved data that I, as Bob, do not have access to, right? So this re-execution problem comes up in a bunch of places, right? Two of which we've seen as examples. However, re-execution is, to a first order, necessary. Let me say why. So in general, it is impossible to kind of figure out the result of a computation without really doing it. There are some results in the complexity theory. These are known as time hierarchy theorems. At a very, very high level, it goes something like this. If you want to determine the output of a t-step computation in time that is much less than t, then that problem is itself undesirable. Okay? That's roughly speaking. It's a beautiful line of work starting a long time ago with Stearns and Hartmanis, and basically says that because we have efficient universal simulation, we can kind of diagonalize against yourself, and you cannot there is no algorithm that will kind of predict the output of another algorithm in general in less resources than the algorithm itself. Okay? And this is even an unconditional result. It is one of the very few precious things that we know are literally true in complexity theory. They are not just believed to be true. Okay? So the takeaway is that more time really does give you more power in terms of computation. And in general, yeah, we're kind of stuck with re-execution as stated. This takes us to cryptographic proofs. Okay? So in our kind of goal to avoid re-execution, we realized that actually the design space that we operate within is a little bit bigger than what kind of the limitations of time hierarchy theorems give us. We can evade this type of results by realizing that the party doing the computation can actually give us some help. They can attach a correctness proof. All right? So we can ask, in this case, Alice to not only perform the computation, but also do some extra computation, some extra proving that corresponds to running some prescribed prover algorithm to produce a certificate of correctness, pi. And then the claim will be accompanied by this proof, okay? This kind of additional string pi. And then there is going to be some verification algorithm tasked with verifying this claim. Okay, so now we're not just re-executing, we're not trying to execute a computation that nobody ran in less resources than are allowed. We're saying, look, somebody did run the computation, they did figure out the output, and now they're doing some extra computation to make it easier for others to certify the output. Okay? And this is going to be useful for us as long as the proof that we produce is so-called succinct. This is an adjective that we use in cryptography to denote the following property: that the time to verify a computation through this proof is much shorter than the time to execute the computation itself. Okay? And now for succinctness to be possible, actually we cannot really do this without cryptography. There's other limitations beyond type hierarchy theorems that I cannot talk about here because they're a bit too technical, but basically, given cryptographic assumptions, we can do this. These things are known as arguments in cryptography, and essentially means that either you break cryptography or the proof is kind of valid, like it's doing its job. Because we believe we cannot break cryptography if you use the right assumptions, then you should trust the proof. All right? So these objects have a name. These things are called succinct non-interactive arguments, SNARKs as an acronym, and they basically embody the goal of certifying computations much faster than they can be run. Okay? And this is going to be a kind of the main tool that we go after for kind of solving the problem of re-execution. Okay, I'm going to give some examples of how to use it. Yes, people following, you can just give me a nod if kind of things are sure. Yes, okay. So I'm happy to take questions along the way, but I've been told, like at the end, I have to say, okay, great. So SNARKs are kind of syntactic. So even though it has this kind of awkward and strange acronym, as syntactically they're pretty simple. Okay, you have two algorithms: the prover and the verifier. The prover receives a specification of a computation. In its head, will run the computation and produce a proof for it, after doing some extra work. And then the verifier algorithm will receive the specification of a computation and will just check it. Okay? So, like as a kind of used as a black box, they have like a pretty simple kind of interface. All right? It's just two algorithms. And this algorithm is something that many people can run. Okay? It's kind of publicly verifiable, as we say in cryptography. And yeah, really, you need some sort of public parameters for the system to run, but kind of that's it. And even the security property is easy to articulate. Let me try to say it. If the computation is correct, then the proof should be valid, right? And if the computational claim is not correct, then it should be computationally hard to produce a proof that will fool the verifier. These are the two sides of a so-called proof system, completeness and soundness, okay? True theorems have proofs, false theorems do not. In this case, more precisely, false theorems do not, you cannot find efficiently valid-looking proofs for false theorems. Okay, that was kind of a cryptographic equivalent of soundness. And you want these proofs to be short, kind of like the size of a hash function. Like think about you hash a big file into a small output. Here we're hashing a big computation into a small proof, some proof that has size that is just the security parameter. Okay. Now, more generally, sometimes we care about privacy, so there might be some secret inputs to the computation. So that's some additional input W, kind of secret. And then we need to require additional properties. How many of you have heard of the word zero knowledge? Right, some of you, okay? Wow, so many. So you also want this proof with zero knowledge. For privacy applications, I will not get into it, but roughly speaking, you want the proof to not leak information about the private data, okay? So these are what SNARKs are. Academically, they are a really kind of beautiful subject. They have a very kind of glorified history going back to kind of big revolutions in complexity theory of all things, where in the 80s and 90s, complexity theorists re-envisioned the classical notion of mathematical proofs in a sort of more modern probabilistic sense, known as probabilistic proofs. Some names that you may be familiar with, like interactive proofs, multi-proof interactive proofs, probabilistically checkable proofs. These are all different types of models to kind of talk about completeness and soundness for theorems. Okay? And to make a long story short, it is a long story. I teach an entire semester about these things. Some of the students here in the class are here and they know very well. It is a long story. But long story short, these probabilistic proofs, through a host of very beautiful techniques like arithmetization and local to global phenomena, quite directly lead to SNARKs. Okay, and this is one of the big achievements of kind of collaborations of complexity in cryptography, that in the 90s we already had SNARKs. However, at the time there was no practical impact. Okay, and part of the reason is that they were so-called galactic algorithms. They had decent asymptotics, like kind of polynomial and stuff, or even kind of polylogarithmic type of things. But then when you look at the actual constants, the actual dependencies, the nice asymptotic behavior would be perceived at input sizes that maybe would be like the size of the galaxy, right? And so it would not be an asymptotic behavior that you would benefit like on the problem size that we care about, say on this planet, within our lifetimes, okay? So, yeah, so it's a great start, okay? But we couldn't really milk these great theoretical results. What has happened, though, is a bit of a SNARK renaissance, that over the last 10 years, there's been extraordinary progress in the cryptographic foundations, efficient constructions, implementations, and applications of SNARKs. And what we have today is that SNARKs have become a basic building block in the real world for blockchains. So if one of the main pillars of blockchains is consensus protocols, these are protocols that let peer-to-peer networks coordinate on the sequence of events, these transactions. The other building block is SNARKs that let us make computational claims that have happened off-chain, so that on-chain you only record the proof that contains no private data and it's easy to check by everybody else. Okay? So this is what has happened, and with the remaining, how many minutes? 5, 10? 5. 5 minutes. I want to illustrate how, for instance, SNARKs have changed scalability in blockchains. Specifically, we're going to go back to the re-execution problem in Ethereum and see how does it play out there in the real world. So, again, to come back to the beginning of the talk, in Ethereum, the same computation is re-executed by many nodes. Right? So there is one block that is proposed by one of the nodes. Everybody else has to check it, or at least a majority of the nodes, according to some notion of majority, before it gets approved to be added to the kind of official log of events. Of course, the first natural thing to do would be to say, okay, we have a SNARK, great. Just attach a SNARK to that computational claim, right? So the node claims the result of A on X equals Y. Here is a SNARK that attests to this computational claim, so that all the other nodes, rather than rerunning the computation, are merely tasked with running the SNARK's verifier, which is going to be much cheaper than the original computation. This works. Actually, it's great. Okay? And however, for making useful systems, it's not quite enough. And the main reason is that the kinds of computations that people have in Ethereum are more like, not like one user, here's a big computation, but it's more like many users, simple computations. Maybe it's like a simple payment or a trade, a simple smart contract call. Anyways, they have to pay for those computations, so there are kind of many simple events. Okay? So SNARKs don't work like to you get more and more benefits of the saving of verification over execution the bigger the computation is, right? So what you really want to do is you want to capture even greater savings, and the idea is you want to batch many transactions into one enormous computation and run a SNARK on that. Okay? So even though this is a proposed architecture is rather simple, what people do in the real world is actually something a little bit different. These things are called SNARK-based rollups. Okay? Let me unpack that for you. Roughly, the idea is that you're going to have users, rather than directly submitting kind of events to the peer-to-peer transactions to the peer-to-peer network, they're going to send them to a untrusted middle person, a service operator. Okay? This service operator is going to gather regularly batches of transactions. Okay, so think of, I don't know, 1,000, 10,000, 100,000 transactions, put them all together, form a huge computation, produce a SNARK that reflects the state transition of all of those transactions applied together, and then propose a transaction that reflects the transition of all of these transactions together. So you have this old state old application state and new application state. They don't differ by one transaction, but by many, many transactions proposed over like a window, say maybe 10 minutes or something, right? So now, instead of processing end user transactions, the blockchain is processing one SNARK proof that attests to a batch of transactions. The roll-up name is kind of like this kind of idea that you have like this burrito and you wrap it up, you roll it up with all the transactions in it at once, right? Now you can go even further and say, look, I'm going to not even publish the application state. I'm going to publish like a short commitment to the application state, and the application state is going to live off chain, right? And so you don't even have to pay on chain for the data of the application state, and you have it kind of secured in some sort of other kind of fault-tolerant system. Okay? So that is an example of a SNARK-based solution. Does that make sense? Now, architectures, in the real world, of course, there is many other concerns. I just spoke about batches, so the first thought should be, wait, what about latency? Like as a user, I don't want to have to wait necessarily 10 minutes to wait for the batch to complete to see this reflected in the chain. So then we kind of build this kind of a transitionary state where it is covered by the service operator during that moment. And then if the service operator were to kind of go offline or kind of disappear in the middle of a window, then you have so-called escape hatches to kind of recover your previous kind of secured state, right? So there's ways to kind of deal with the optimistic, let's say, a kind of system design within that window, right? But every 10 minutes you have like a proved transition state. These things are used a lot out there, like every day, and they have been for now a couple of years, and they work exceedingly well. They're a very powerful bootstrapping mechanism to kind of increase the throughput of a blockchain. 2 minutes? 1 minute. 1 minute. Okay, so I'm going to fast forward. I'm going to skip what I talked about. I could have talked about privacy, but I'm going to skip and talk about the kind of things that we don't know about SNARKs. Okay, I'm going to the screen. Wait, I don't know to do the full screen. So, 10 years is very short, obviously. Went from like theory to practice. 10 years is still pretty young technology. There's lots of questions that sit very squarely at the intersection of cryptography, complexity, and security that can still have like major impacts to the applicability of SNARKs. I'll give like some examples. So one is like these rollups, right? So these are just architectures that came up in the last 4 or 5 years, but as systems, maybe one can do like much better. Okay, their latency, you can mitigate it with these intra-window trips and kludges, but there's still problems, especially if you store the entire data off-chain. Now you're left with this so-called data availability problem. Where is the data sitting? On another blockchain? What about that one? Right? Here's another basic question. So many of these SNARKs actually require large amounts of memory to run the program. And so you're kind of limited on how large of a computation you can prove, even if you're willing to wait. We can scale to billions of logical gates in terms of the size of the largest computation, but we can't get to trillions. It's currently out of today's techniques. What could probably get us there is streaming provers. Okay, it's a small space algorithm that can run for a long time, maybe in parallel, but you don't have to allocate enormous amounts of memory. Theoretically, we don't have very good streaming solutions at the really theoretical level. Great foundational question. And one of the questions I am personally sort of very excited about is kind of thinking way ahead, kind of what kind of SNARKs will we use, let's say, like a few centuries. Digital infrastructure is very sticky. Right? Like, so there's a lot of things about the internet that we would like to change, but we can't because it's deployed, right? So if we figure out now, before SNARKs kind of colonize too much of the digital infrastructure, it's a great time to put in place SNARKs that will remain secure for a long time. And there are constructions that plausibly are secure in a very strong sense, but they're not as efficient as the ones that maybe are, let's say, not quantum secure. And so a lot of the things I care about, and I like to collaborate with my students and colleagues, is on the kind of post-quantum nature of SNARKs. I think I'm going to stop here and take questions. Yeah.